Welcome to another tutorial of ProfLearn YouTube channel. In this video, I'm going to take you through the physics prediction that I give out, and I'll take you through how you're supposed to answer those questions, the best practice, some of the concept that you ought to remember. So we shall be having a walkthrough which will enable you prepare well, and if there is any area that you have forgotten, you'll be reminded. Here is a model answers for that is coming from ProfLearn. And if you're new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload the second section of this paper, you'll be notified. You can also check in the description below so that you can be able to download this document I'm having here. So the first question that was said here, we were told that two identical springs, S1, S2, are suspended from a fixed support. Masses are attached to the bottom of S1 and S2 as shown. And can see here, I brought to your attention some of the formulas that are quite important in this topic. You need to remember that force is equals to spring constant times extension, and this is what we call now Hooke's law. And you need to know how Hooke's law states. Hooke's law said that extension is directly proportional to the force applied, provided the elastic limit is not exceeded. And if a material obeys Hooke's law, you are going to have a straight line graph for force against extension. And if you work out the gradient, or you work out the slope of the straight section of the graph, you are going to have what we call the spring constant. And this point here where you are evaluating your spring constant is called the limit of proportionality. Then the graph, if you continue adding the force, the graph is going to change, and then we shall have something we call now the elastic limit somewhere here, which means that beyond that point, the material is going to undergo plastic deformation. And we said plastic deformation, we mean that a material does not regain the original shape once the force is removed. So that's why you're gonna see that the graph now maybe will just come like this, and it will just reach here, meaning that it does not regain the original length. It will show some extension the moment the material or the spring is offloaded. And some other areas, some other concept that I usually asked is what is the amount of energy, elastic potential energy stored? Elastic potential energy stored is area under the graph. Or you can be able to use the formula elastic potential energy stored is equals to a half force times extension, or it can be energy equals to a half k x squared. So from the graph, you work out the area under the graph. And maybe if you are asked the energy that is wasted when it's loaded, you will see that when unloading, during unloading, this is the area under the graph. But when it was being loaded, there was also this section. So if you are asked the energy wasted, it will be the area under the entire section, entire shape. You remember square counting techniques, and then you subtract the area of this one. So this region here represents the energy that is wasted in other forms such as heat. All right, let's go down and get to see what's the question asking. Which of the following is the elastic strain energy in spring 2? Now we know that energy is equal to a half Fx, right? And for spring 1, we have the mass m is the one that is stretching this spring, and the extension there is given as x. So we have energy equals to a half mx, because the extension is x and the force is m. And remember, force is also proportional to mass is proportional to force, so we can be able to use m here. So from this first equation, we can be able to rearrange this, and we shall say that we are going to say that mx equals to 2e. Because you multiply to both sides, we shall have this equation. Mx is this. Then we go and work out the energy for S2. S2 is going to be the force, our force now is 2m, and the extension is x over 3. So this is the information we get. But mx that we are having here is representing 2e. So we can be able to say that a third 2e, a third times 2e, and that is going to be 2 over 3e. So meaning this is the expression we shall get for energy stored in string 2 in terms of the energy stored in string 1, and that is the option C that we are having here. So you need to understand that you can be able to be asked question to do with calculating the energy stored in a spring, either by calculations or by multiple choice like this one, or you can also be asked to work it from the graph. A lamp with efficiency of 0.68 usefully transfers 120 joules of energy. Which of the following can be used to determine E and the energy supply of the lamp? This question smells like it's coming from the topic work, energy and power, and especially efficiency. Now, efficiency is given out by this formula, and useful energy output is the value that we have here, and the energy input is what we are being asked. All right, but if it was given in percentage, we could have multiplied by 100% here. But now, since it's just a decimal like that, a ratio like this, we are going to say 0.68 is equals to 120 over E, and making E the subject of the formula that tells us that the answer is D. Now, you learned about equation of motion, so you need to remember these equations of motion before you sit for your exam. The first equation of motion is here: v equals to u plus at, s equals to ut plus a half at squared, v squared equals to u squared plus 2as, and the final one is s equals to u plus v over 2 times t. V represent the final velocity, u represent the initial velocity, our a represent the acceleration, and we talk about t as the time taken, and s represent the displacement of the object. Now, a ball bearing falls vertically from rest. We have a ball falling from some height, and it falls through that height, whereby it takes a time of 0.32 seconds. And then we are told that the distance over which it falls, or the height, is 50 centimeters. Of course, when we're dealing with the equation of motion, remember we are talking about constant acceleration, and then our unit must be in SI unit. So this has to be divided by 100, and that is going to translate to 0.5. Now, if we were working out the expression that gives acceleration, we can use which equation? We're going to use the second equation because it has acceleration that we are finding, it has the displacement, it has the initial velocity. Initial velocity, remember, it's starting from rest, is 0 meters per second. So, and it has time. So this is the equation that has all the quantities. Then we can be able to rearrange that, and our answer becomes A. Our answer becomes A. I believe you are getting value from this video. Consider sharing this video to your friends. Encourage them also to subscribe to join the ProfLearn family, so that when we are going to do other units, once you are done with unit 1, you'll be moving to unit 2, so that we are in the same house. We shall be learning more of this. Now, sometimes you'll be given arrangement of springs, and springs can either be in series or can be either in parallel. And the key formula that you ought to remember in this topic, you need to remember that force is equals to kx, and that is what we call what? This is what we call Hooke's law. And the second formula that is very important is also energy equals to a half fx, or this can also be given as energy is equals to energy is equals to energy is equals to energy is equals to it's making give me trouble, giving me trouble. All right, so energy is equals to a half k e. All right, let me just use x for consistency as extension of kx squared. So, which of the following expression gives elastic energy stored in the parallel system? But we are told that in certain spring, when a certain spring stretched by tensile force F, the force, remember, is F, so energy stored in that spring is what? Is E. Now, three of these springs are arranged. Three of these springs, so meaning there is the same spring constant we're talking about as the initial one, are arranged in parallel and stretched by the tensile force 2F. So what do we understand when springs are arranged in parallel and are stretched by a given force? All these springs that we're having here, they're going to share the force that we're having here. So this spring will be stretched by 2F over 3. This will be 2F over 3. This will experience a force of 2F over 3. But if springs were in series and there is a force of 2F stretching them, it means this one will experience the force of 2F and this one will experience a force of 2F. We're gonna talk about this later in the next part. But let us focus now on this one here that we were given. So we were told that which of the following expression gives the energy stored in the parallel system. So we have to agree that the force for each of the spring here is going to be what? 2F over 3. Now, for each single spring, for the single spring that we were being told, we were told that energy is equal to a half Fx, or energy is equal to a half Kx squared. But F is given by Kx. So meaning that we can be able to get the extension by saying extension is equal to F over K. Are we together to that point? Okay, if we are together, let's move to the next part. Now, using this equation that we had highlighted at this point here, and we have said extension is actually F over K. So meaning we can be able to say energy equals to a half K times, instead of X squared, we can replace this. Then we are going to have energy equals to a half F squared over K, because K will cancel with 1K when this is squared, and we shall have energy is equals to F squared over 2K. But remember, this is a constant. So we can be able to say energy stored in a spring is proportional to the force squared. That's why I am using this equation here, so that I can come up with this relation that energy stored in the spring is proportional to what? To the force squared. So this formula is going to become handy, because if you are having different amount of energy and different amount of forces, we can say energy 1 from this formula. If energy is proportional to F squared, if you have energy 1 over energy 2 is going to be equals to F1 over F1 over F2, then this will be squared. So why am I doing this? I'm doing this from this relation so that I can be able to relate the energy that was stored in the single spring that we were having in the original part. I relate that to the energy that is going to be stored in the single spring in the parallel circuit, in the parallel connection. So we're going to say energy energy in each of the spring in parallel is going to be equal. Remember, energy for the single spring that the question started with was F over the new F that we have gotten here, which is 2 over 3F. Then we square that. We rearrange this equation. We are going to have energy in each of the spring in parallel is going to be 4 over 9. But there are 3 springs, so for us to get the total energy in parallel is going to be 3 times the energy in each, which we have gotten here, and that is going to be 4 over 3 times 4 over 9e, and finally our answer becomes what? Our answer becomes C. Answer becomes C. So let me tell you, these questions whereby we are talking about multiple choice, even though it's having just 1 mark, it doesn't mean the question is going to be one step. It doesn't mean that. It doesn't mean the question is going to be easy. You need to review on that. And another concept that is highly testable, the highly tested most of the time is the understanding between the difference between scalar and vector quantity. But we know that scalar quantities have only size but no direction, but vector quantities have both size and direction. So if you look at density, density does not have direction. Kinetic energy does not have direction. Viscosity does not have direction. Then we talk of what? Momentum as the answer. Under projectile motion, you will be also be asked to work out questions, but remember, objects are projected horizontally. In the horizontal direction, these objects are not affected by gravity, so they travel always in a constant velocity in the horizontal direction. Horizontal direction horizontal motion remain constant throughout the journey. But this object, as it's moving, it has 2 motion. There is a horizontal motion, at the same time there is vertical motion. There is horizontal motion in the sense that as it's coming down, as it's coming down, as it's coming down, as it's coming down, you are going to see that as it will be moving away from the platform where it did what? It was subjected for. So the velocity in the vertical direction will be increasing with time. By the time it lands on the ground here, it will land with the greatest vertical velocity, but the horizontal velocity will remain constant throughout. Now the range is going to be the v in the horizontal direction times time, and the time we are talking about is the time to hit the ground. Okay, the time it takes to hit the ground is the same time it takes to land here. So let us see which of the following expression could use to determine the value of S in meters. S in meters. Yeah. So we are going to use the formula S equals to UT. Yeah. Yeah. What is S? S is the range. So of course, for you to find the range, you are going to use the formula here. But we need to know how long does it take to hit the ground, right? And for that case, we are not going to go that direction. Remember, we're not going to go that direction because only we were told horizontal velocity or horizontal velocity was that. So meaning we are just going to go straight and say the ball takes 9 seconds, already it's provided 9 seconds. So we're going to say 1.2 times what? Times this. But if you are finding the height, you're going to use S equals to UT plus a half AT squared. So you are to use this formula in order to find the height. So in this coming exam, you can be asked the question to do with time to hit the ground or to find the height, or the distance the object landed on the ground from the foot of maybe that platform. Also, you can be also be given question to do with uh, projectile motion like that, projectile at angles, projectile at angles. So you have to be prepared on that. But for projectile motion, if you have an issue with answering question with projectile motion, I've added a link in the description where I explained how you should work out a question to do with projectile motion. Just check the link in the description so that you go straight to that video so that you can be able to learn upfront, prepare for this exam. Remember, a lack of preparedness is preparing to fail. So check in the description. There is a detailed video I did on projectile motion, and it's very much details. You can be able to access the PDF even. So check in the description so that you can be able to learn that. Now there's question to do with motion in inclined plane. So motion in inclined plane is here. Quite interesting. An object accelerates from rest down a frictionless slope. The object moves a distance of 20 meters, and the slope is at an angle of 23 degrees to the horizontal as shown. So something that we ought to remember, if this angle is 23 degrees, then it means that this angle is also 23 degrees. No, let me just show you. It's just simple. Let me just show you using this explanation. If this angle is, let me use, if this angle is 30 and there is a box resting here, yeah, so we know that weight will be acting vertically down. I'll want to switch it here. Let me just put it here. Weight will be acting vertically down like that. And then the inclined plane will be exerting a reaction force here. This is normal reaction force. And then we shall have the action force. The force the box now or the block of wood is exerting into the inclined plane. So now, if this is 30 and weight usually acts vertically downward, then it means this angle that we have here is what? Is 90 degrees. So if this is 90, it means this angle here is going to be 60. But what you need to remember also, this line that we have here forms 90 degrees at this point. So if this is 60, what will be this angle here? This angle will be 30. So that's why anytime you are given motion inclined plane, if this angle is given here as 23, then the angle between the vertical line and the normal line that is straight into the inclined plane should be 23 degrees. Now, we are going to analyze the final speed of the object down here after covering a speed of what? 20 meters per second. There are different ways you can be able to do it. You can be able to use equations of motion. Yeah. Then, but we know at what speed, what will be the acceleration of this object down the inclined plane? What we know is the acceleration due to gravity. The acceleration due to gravity will be acting vertically down. So we need to resolve that so that we have the component of gravitational potential energy, which is parallel to the inclined plane. And the component that is parallel to the inclined plane is this one. So if this is G and this is 23, this is the hypotenuse, and this is opposite to the angle, then we can say now this one is G sine 23. So this is also going to be G sine 23. So this box is going to be sliding down 9.81 times 9.81 sine 23. That will be the acceleration due to gravity now in the direction of the inclined plane. That is how this box will be sliding. That's the speed at which this box will be sliding down. That's how it will be sliding at that particular acceleration. So what will be the speed by the time it's going to land down here? That's the question that we are being asked. So we are going to use the formula V V squared equals to U squared plus 2AS. V squared equals to U squared plus 2AS. Remember, it started from rest. At this point, it started from rest. So which means that we can be able to substitute our acceleration 9.81 sine 23 times the displacement that it moved in order to get it. And we shall get our option, and our option will be C. I believe we are together up to that point. When compressed by force, when it's compressed by force of 50 newtons, the spring had a length of 1.2, rather that is 12 centimeters. 12 centimeters. Now I need to take some water so that I can be able to proceed and say what is it. Are you getting value from this video? Just let me know. Let me know so that I can be able also to prepare more. Just let me know. Yes. Let me know if you are getting value, and also just take this point to subscribe if you have not subscribed, because most of my viewers, they have not subscribed, and I don't know whether they are you unhappy with my tutorials. Just let me know. If you subscribe, if you like, if you leave a comment down below, I'll be able to know you are enjoying the lesson, and I can be able to work more on that. Now, when compressed by force of 50 newtons, a spring had a length of 12 centimeters. When compressed by force of 70 newtons, the same spring had a length of 7.1 centimeters. Which of the following expression that gives stiffness K of the spring in Newton per centimeter? Let the original length be L. That's how I started by looking at that question. And the spring constant K is change in F over the change in extension. Yeah, because we are using the formula. We've talked much of the springs. We have used the formula force is equals to Kx, and then we can be able to rearrange spring constant is equals to F over what? F over X. So which means that spring constant is going to be change in F over change in what? In X. Now, if we are talking of the extension for 70, remember the original length was L, so the new length becomes 7.1. So meaning is L minus 7.1. That will give us the compression, yeah, by how much did compress, which is the same as, remember, compression is proportional to extension for springs, and for X extension for 50 newtons, it will be 11 LL rather minus 12. Then change in extension, it will be this one minus this one, and then we shall have change in extension. Remember, this is L minus L. L is going to cancel out. Negative 7.1 minus negative 12, it becomes negative 7.1 plus 12, because this sign and this sign becomes a positive, right? This smells like algebra in maths, huh? Right? Integers, huh? Right. Then now the change in extension here becomes 12 minus 7.1. And then change in force, of course, is 70 minus 50. So using this relation here, we can be able to say that extension is change in F over change in what? X. Then our answer is B. A rocket is accelerating horizontally due to the constant resultant force. The mass of the rocket decreases steadily as it uses its fuel. Remember, as the mass is decreasing, the force is constant, then it means acceleration is going to be increasing with time, and we're going to say our answer is B. B. Question 10, equilibrium. Condition for equilibrium: upward forces should be equal to downward forces. So if there is this bar that is resting at this point, and we can be able to draw a line like that, and we shall have 90 degrees here. Tension tension at this point, and we told that the angle here is what, 80. So if this is 80, then this angle also is going to be 80. Now, what will be the vertical component of this tension? You see, as this string is pulling in this direction, there will be a vertical component, and also there will be a horizontal component. But now we are focusing on the vertical component. The vertical component is going to be, even if you just draw it like that, the vertical component will be this one here. So it will be cos t cos theta, or you can even use this one. If this is 90, this is adjacent, so you are using cosocatoa. So t cos theta will be this part, t cos theta. But there are two of them, so there is this one, so we are going to say this answer times 2. Yeah, so 2 t cos theta is going to be equal to w. Yeah, because of equilibrium. But the question, which of the expression is correct? Let's see. So t in the y direction, that is in the vertical component, is going to be this. Total in the y direction is 2 times t cos theta. At equilibrium, total downward force is equal to the total upward forces. So we can be able to say our t is w over 2 cos theta. That is what? Correct. This is wrong. Yeah. Sine, anywhere you see sine is wrong. So, and I've shown why we are using cosine. Yes. Right. So we are having here, we are having, I don't know who's this. Who's this? Yeah, this woman who supports a stationary wheelbarrow by exerting an upward force. So if it's supporting stationary, if it's balanced and it's raised at this level here, it means downward force is equal to the upward force, right? So meaning the downward force is equal to the upward force, meaning the reaction force P, when they're added together, should be equal to the downward force. And I think this is the weight of the wheelbarrow, but we shall look into that. So something that you need to remember is that the center of gravity is defined as the point where all the weight of the object is considered to act. This question might be asked. So explain by considering moments about g why p is less than. Why p is less than? If you look at the distance that we are talking about, the distance from g to where r is, and the distance from g to where p is, p has a larger distance. Yeah, so the force should be small so that the two moments can be equal. Remember, at equilibrium, clockwise moment should be equal to anti-clockwise moment. So, and moment depend on the force and distance. Now, since the distance here is small, then the force here must be large. Since the distance here is large, the force there must be small so that the two moments can be equal. And when you are supposed to respond to that, this is exactly what you are to mention. Moment due to the force R on the wheelbarrow, yes, and the force P on the handle must be equal about any given point. Since the moment of force is a product of force and perpendicular distance from the pivot, the force P is less because the handle is further away from the center, hence less force is required for equal moment of force. The horizontal distance between the center of the wheel and the handle is 1.5 meters. The magnitude of P and R are shown here. So we are told the value of R is this and the value of P is this. We don't know the weight. Determine the horizontal distance between the center of the wheel, the center of gravity of the wheelbarrow, and the wheel. Determine the horizontal distance between the center of the wheel and the center of gravity of the wheelbarrow. Now, remember, this reaction force is at the pivot. This is where the wheelbarrow will be rotating about. So I don't know whether we can be able to do this. the way it was drawn. Yeah, this is our wheelbarrow here. This is our wheelbarrow. That is our wheelbarrow. Beautiful wheelbarrow. Beautiful wheelbarrow. Beautiful wheelbarrow. So meaning that if this wheelbarrow that we are having here, it will be rotating. It will be rotating at what point? It will be rotating at about this point here, about the wheel. That's where it will be. It will be rotating. So the weight will cause what? The weight will cause anti-clockwise moment. The weight will cause a clockwise moment. The handle will be causing anti-clockwise moment. The handle will be causing clockwise moment. The weight will be causing a clockwise moment. And we can say clockwise moment is equals to clockwise moment. So in that regard, we are going to say that since the wheelbarrow is at equilibrium, the upward forces and downward forces must be equal. So if you add this force and this force, these are upward forces must be equal to the one downward force, which is the weight. So the weight of the wheelbarrow is 400 newtons. Then we're going to use the principle of moment. Remember, principle of moment states that at equilibrium, the sum of clockwise moment equals to the sum of anti-clockwise moment. So remember, all the distances must be measured from the point of action of the force to the pivot. So the perpendicular distance from where the weight is acting to the pivot, the distance from the line of action of the force to the pivot, our pivot is going to be here, is x. So we shall say 400 times x. And the perpendicular distance from where the pivot is to the line of action of the force is the 1.5 meters. So we shall say 1.5 meters times 80, or 80 times 1.5 meters. So working it out, we are going to get 0. What? 0.0.3, and the horizontal distance is actually 0.3. Then we need to transfer this here so that we can be able to make the examiner happy. Okay. A steel object is held by an electromagnet, and the magnetic force prevents the steel object from falling. State two reasons why the weight of the object and the force from the electromagnet are not Newton's third law pair. So you need to remember this condition, that Newton's third law, Newton's pair, third law pair, the forces should be of the same type. The forces should be of the same type. Condition number two, they must be acting in different objects. The forces must be acting in different objects. The forces must be equal and in opposite direction. The forces do not cancel each other. Then the forces now state are not. Why are they not? Because they are not satisfying this condition that I've written here. Can you write it down? Write it down. Then the forces act on the same object. We said they should be acting there. They should be acting in different, or they should be acting on different objects. They should be of the same types, should be equal and opposite direction. But here, what is happening? They are acting on the same object, right? They are not the same types of forces. They are not the same types of forces, right? Okay. Electromagnet is suspended from a support by a steel cable, as shown there, and that is materials. Remember, stress is equals to force over cross-section area. Strain is equals to extension over the original length, and the Young's modulus is stress over strain. So if you are going to have the graph of stress against strain, if the straight line, the gradient of a stress strain graph is going to give you what? It's going to give you the Young's modulus, okay? Young's modulus will be giving you Young's modulus. And the area under the graph here is going to have strain energy stored per unit volume, right? I think you need to also check in the description. Check in the description. There is a video I did fully questions that have appeared in different exams on Young's modulus. I did all the questions. So check in the description, go there, watch that video, and also download the PDF involved with that. So that is why I brought this to your attention, so that I can also remind you, you go and check them, right? So in this particular question, this is what you are supposed to do. Yeah, so watch out for the next part of this paper and check in the description. Go straight to those topical questions I did for projectile motion, for Young's modulus, tutorials, Young modulus and projectile motion tutorials, so that you can be going through as you are waiting to see the next video. And also check for the part 2 of this paper in the description, so that you can prepare well for this coming exam. Good luck and all the best. See you in the next.